Hello everyone, my name is Sahil Bhatia. I am Assistant Professor in Department of CSC AI and ML. In this video, we will be discussing about stack data structure. By the end of this video, you will be able to define what a stack is. You will be able to understand the last in first out principle. You will learn about various operations of stack, and you will also be able to explore various real life applications of this data structure. And finally, you will all be able to analyze the time complexity of various operations of stack. So let's get started by what is a stack. So stack is a linear data structure that follows last in first out principle. That is, the element to be inserted at the last will be the first one to be removed. Imagine you have a pile of books placed one over the other, and you can remove books from only top of the pile of the books. So if you place five books over one over the another, and if I ask you to remove the book from the top, which book will you remove? Well, the answer is simple. The book which you kept at the last will be the first one to be removed. You can see in the slides that allows insertion at the top, deletion at the top, and access is restricted in the sense that only top element of the stack is visible at all the times. You cannot access any other element of the stack except the top. Now, let us understand what is LIFO or last in first out operation. So imagine you have a stack of plates and your task is to put one plate over the another. Earlier, the stack is empty. That is, you do not have any plate in the stack. Now, in step 1, you place plate A on the stack. Then you place plate B on the stack, and at the end, you place plate C on the stack. Now, since you place plate number C at the end, meaning currently at top of the stack, you have plate C. Now, if I ask you to remove an element, that is, remove a plate from this stack of plates, which plate will you be able to remove? Well, the answer is again very simple. You put plate C at the end. Now, you have to remove plate C from the stack. Now, plate C is gone from the picture. Remaining, we have plate B and plate A. Now, remember, in step 2, we put plate B, and in step 1, we had put plate A. So last plate to be entered among these two was plate B. So currently at top will be plate B. So if I ask you to remove an element, that is remove a plate from the stack again, you will remove plate number B. And finally, again if you perform the uh, removal operation, you will remove plate number A. Now stack is again empty. Let's look at the push operation. So whenever you add an element in the stack, we call it a push operation. So in a stack, push operation always takes place at top of the stack. That is, push adds a new element at top of the stack. Imagine an example where you have in the stack elements 10, 20, 30, and 40. So currently imagining element number 40 is at top of the stack. Now, if I were to add another element using push operation, say 50. So if I add an element 50, the top index would be incremented, and at the new index the element to be inserted will be 50. So after the push operation, the top element of the stack will be 50. Now let's talk about pop operation. So pop operation, basically what does it do? It removes the top element from the stack and returns it. Consider an example where you have elements in the stack 10, 20, 30, 40, and 50, and top element is 50. So now what will pop operation do? It will remove the top element. What element is at the top? Element number 50. So what will pop operation do? It will remove element 50. It will decrement the top index. and then return the element 50. Now, after pop operation, what will be the new top element? It will be 40, right? Now, let's talk about another operation in the stack called peak operation or also known as top operation. Now, imagine you just want to check the top element of the stack. You do not want to remove it, you do not want to add anything, you just want to look at the top element. So, for this, we have peak operation. Peak operation, what does it do? It looks at the top index of the stack. It returns that element without removing it or without doing any manipulation with the stack. It will just return the top element. So for example, if you have a stack 10, 20, 30, 40 with 40 as the top element, your peak operation will return element 40 and top index will remain as it is. So peak operation is a non-destructible operation, meaning in peak operation, stack is not changed at all. You can think of it as a read-only operation. Now let us look at some of the real-life applications of stack. Have you ever imagined whenever you click a back button in the browser window, you are redirected to the previous page that you explored? How does it happen? Well, in a browser, all the pages that you visit are pushed into the stack. So again, remember the LIFO principle. The last page you visited will be present at top of the stack. So whenever you click a back button, you are automatically redirected to the last page that you had visited. Various tools such as Microsoft Word use your progress in a stack. So whatever you type, the last word to be typed is stored in a stack. Now, whenever you click an undo button, the last element from the stack will be removed. So that word will be removed from the MS Word. Now, if we talk about function call stack, you might have studied in C programming language that whenever a function is called, it is stored in a stack and it is present in the stack as long as the function is being executed. Once it is executed, the function is popped from the stack. Imagine you have to evaluate various expressions such as postfix expressions. You use stack for evaluating the postfix expression. Various graph algorithms such as depth first algorithm. Depth first search algorithm uses stack to store the nodes which are to be visited to search a particular node. So imagine how vastly stack is used in your real life examples. Now enough of the theory. I know you would have been bored by the theory till this point. So let's look at some implementation of stack. So we studied three operations in a stack: push, pop, and peek. Now, as you can see on the slide, you can declare a variable stack with a max size. So you can give max size as 100 in stack. The top element in the beginning would be -1 because array indexes start from 0 to n. Since this is a array implementation of stack, top has to be -1, meaning initially stack is completely empty. When you look at the push operation, you can see here void push int value. So push operation takes one parameter only, that is value to be inserted in the stack. So you can see a if condition here. What is this if condition checking? Well, this if condition is checking the overflow condition, meaning whenever you want to insert an element in the stack, you have to check whether the stack is completely full or not. If stack is completely full, this is an overflow condition. You cannot add any new element in the stack. If overflow condition is not there, as in this code, you will have to firstly increment the top index, top variable will be incremented, and that at that incremented value, at that incremented index, you will store the value. Now let's look at pop operation. How does pop operation? Pop does not need any argument. It automatically gives you the top element of the stack. How does it do? Firstly, whenever you want to delete an element from the stack, if I ask you to remove a book from the stack. If there is no book in the stack, what will you remove? Similarly, that is underflow condition in stack. If we have to remove an element from the stack, firstly you have to check whether stack contains any element or not. If stack contains some elements, then you are good to go. You can remove the top element. So what you have to check? You have to decrease. First, you have to remove that element from the stack, top of the stack, return it to the user, and at the end, decrement the top operator, top variable. Now, after decrement, the top variable will be pointing to the new top of the stack. Peak operation, again, you want to display top element of the stack. Again, you have to check underflow condition, because if there is no element in the stack, what will you display, right? So you have to check underflow condition again here and just return the top element of the stack. So this is implementation of the stack which you can practice on your own. Now let's look at performance analysis of the stack. You will be surprised to know that core stack operations like push, pop, and peek, they take constant time, meaning these operations can be performed in constant time. Does not matter if you have 10 elements in the stack or 10 million elements in the stack. You can always perform these three core operations of the stack in a constant time. Imagine the utility of this stack data structure. Well, if you want to search an element in the stack, you have to go through all the elements of the stack one by one. So the time complexity of searching operation in a stack would be order of n. So this brings us to the end of this video. Now let's us look at some key takeaways. What have you learned? As promised at the beginning of the video, at the end of this video, you will be able to recall what will be a LIFO principle, what are push, pop, and peak operations. You have seen the implementation of stack, and you have seen the efficiency of the stack operations. Thank you.